Okay, so today, students, we are going to go into study the nature of sound, and it's our second out of three chapters on this subject of waves and sound. And we are going to study mostly what you see here in these items. So the basic idea we want to cover is how sound is produced, how it gets transmitted, how we quantify it in terms of its wavelength and its frequency, and also its speed. So we will talk about this as we go through. Origin of sound. Now, most sounds are waves produced by vibrations of matter. We've talked about that with tuning forks. We can also, stringed instruments can cause these vibrations of compression. I call them compressions of air molecules. So string instruments are one way of generating sound. Obviously, the vocal cords in our voice are also vibrating at frequencies that allow our ears to hear that, and those are the frequencies that we have been discussing. In a flute, by a fluttering column of air at the mouthpiece, another way of generating sound is through wind instruments. And we'll discuss a few other cases as we go through. Trying to think if there was one more thing, but it'll occur to me later, maybe. Okay. So, origin of sound. The original vibration stimulates the vibration of something larger or more massive, such as the sounding board of a stringed instrument. And by that, what we mean is, if we take a guitar, the string vibration produces a low volume or low amplitude wave, but in order to hear that over large distance, it's connected to this wooden structure, which we call the guitar, and the reverberation of those air molecules, or the vibration of those air molecules, once they get inside the instrument, cause the entire wood to vibrate at that frequency, and therefore we get a much larger volume coming out, because now we're not just compressing air molecules along a thin string, but we are compressing air molecules at a frequency over the entire surface area of a large instrument. And violins will do the same thing, cellos will do the same thing. It's the transmission of the vibration of the air molecules caused by the string that gets sent into the wooden structure of the instrument that causes it to vibrate at the same frequency of the string. And so that structure, whether it's the cello or the violin, or the wood of the cello, the wood of the violin, the wood of the guitar, acts as an amplifier to amplify the sound. And so this vibrating material then sends a disturbance, which we now recognize as a compression of air molecules at a certain frequency through the surrounding medium, usually air, in the form of longitudinal sound waves. So as we've said before, the sound waves are made of longitudinal waves. They are compressions and rarefications of the air molecules that are traveling in the direction of the velocity of the sound itself, and therefore we call that a longitudinal wave. The frequencies of the source, namely the string, and sound waves are the same. So what this is saying is that if the string of the instrument is vibrating at 400 hertz, then the compressions of the air molecules will also be at 400 hertz, and you will hear directly the same frequency of the vibration on the string that is produced in the air, and which is therefore produced in your eardrum. So these frequencies are the same. The subjective impression about the frequency is what we call pitch. So high pitch and low pitch are basically different names for high frequency and low frequency. Now, the ear of a young person can normally hear pitches in the range of 20 to 20,000 cycles or compressions per second. And as we grow older, then the limits of the human hearing shrink, and especially at the high frequency end. Sound waves with frequencies below 20 hertz are called infrasonic. Sound waves with frequencies above 20,000 hertz are called ultrasonic, and these are too high for the hearing of human hearing. The infrasonic, are too low, and you may have heard a lot about ultrasound as a medical device for imaging, which we'll talk about a little bit later, but generally we cannot hear those frequencies that are either too high or too low. Now, another way to produce the sound, which is very effective, is the use of speakers. So speakers are vibrating membranes that vibrate at the frequency of the sound being produced. So they are very thin, paper-like membranes that oscillate back and forth very, very rapidly, and the frequency that they oscillate at is also the frequency of the compressions observed at a known location, which is how many compressions per second are being observed at the microphone. They can travel through solids, liquids, and gases. The velocity depends on the medium, but maybe surprisingly to most of us, the velocity of sound through heavier objects is faster than the speed of sound through less dense objects. So for example, the velocity of sound in water is several times higher than the velocity of sound in air, and the velocity in steel is higher than the velocity of sound propagating through water. So this just gives us an idea of how sound is produced and what its speed is. So as we've talked about before, we produce the sound waves by the oscillation of an object that's compressing the air molecules. And when these compressions move away from us, we get a string of compressions or compressed air, which are at regular spatial intervals as they move down the tube from left to right. And this spacing between these compressions, or the maximum compression in one location compared to the maximum compression in another location, determines the wavelength, the spacing between them. So we could either determine them as the spacing between compressions or the spacing between rarefactions. So a loudspeaker is a paper cone that vibrates. It vibrates at the frequency of the sound, which is the frequency that we hear it at, that the air molecules next to the loudspeaker get set into vibration, just like the pitchfork caused the compressions and rarefications of the air. So too does the paper cone produce the compressions and rarefications traveling in air. And the sound waves reach your ears, setting your eardrums into the vibration at that same frequency, and therefore sound is heard. In this case, a microphone picks up the sound, and it translates the compressed air or air compressions that is a mechanical feature into an electrical signal. Media that transmits sound. Any elastic substance can transmit sound. In elastic liquids and solids, the atoms are relatively close together. They respond quickly to one another's motions and transmit the energy with very little loss. If you go to gases, the atoms are far from each other, therefore they respond. It takes a longer time for the compressions in one region of space to reach the compression, to produce the compressions in another region of space. And so that energy gets transmitted much more slowly, and so air has a slower velocity, produces a slower sound velocity than liquids or solids. And as we indicated before, the sound wave in in water is about 4 times faster than air, and about 15 times faster in steel than in air. So the more dense materials have a much higher sound velocity. This is an important thing to keep in mind. The speed of the wave will, in ordinary air atmospheric conditions, will depend on, of course, wind, temperature, and humidity, as well as pressure of the air in our environment. Now, normally at sea level, or very close to sea level, in dry air, we have a speed of sound that's measured to be about 330 meters per second. That's roughly the same as what I quoted earlier, which was 750 miles per hour. And warm air transmits sound at a higher speed than cold air. So the more cold or the colder the air is, the slower the propagation of the velocity of sound. Now, each degree rise in temperature above 0 degrees, which is the freezing point of water, 32 degrees Fahrenheit, will increase the speed of the sound, or the sound wave, by about 0.6 meters per second. And of course, the Concorde is the one we talked about in the last chapter. Another important feature of the Concorde was that it was often advertised as an airplane that could go twice the speed of sound. Well, if the speed of sound was 750 miles per hour, but it was only traveling at 1,350 miles per hour, it is clearly not twice the speed of sound as quoted here. But the important thing is that the speed of sound goes, even though the airplane is not speeding up as it goes higher altitude, well, it does that also. But the important point is that the speed of sound is dropping by 0.6 meters per second, and it's 93 degrees centigrade cooler at the higher altitude. So the speed of sound is, by the time you get up to an altitude of 60,000 feet, is only about 270 meters per second, as opposed to the original 330. So now it's only, the speed of sound is more like 600 miles per hour, because it is speed of sound at the altitude of the airplane, and at the altitude of the airplane, it's 93 degrees colder. Therefore, the speed of sound will be dropping by 93 times 0.6 meters per second, giving a lower velocity. And now we can say that it is traveling at twice the speed of sound at the altitude at which it's flying. So the speed of sound does go down as you go to higher altitudes, because of the fact that as you go to higher altitudes, it's also colder, and colder air has slower velocity of sound. So here's a quick check you can do to see you understand the concept of velocity. You watch a person chopping wood, and note that after the last chop, you hear that 1 second later. How far away is the chopper? Well, there's a few choices here. 330 meters, 330 more or less, more than 330, less than 330. No way to tell. Well, what we can indicate is that if we assume that the velocity of light is far greater than the velocity of sound, which it is, light travels at a speed of 186,000 miles per second. So that's about 300,000 kilometers per second. And so we basically can see the chopper instantaneously. But if it takes 1 second for us to hear the sound, we know that it was produced 1 second earlier. And if the speed of the speed of the sound is 330 meters per second, then it should be It should be 330 meters away, right? Because that's how long it takes a sound to travel. And sure enough, we find that the answer is 330. You hear thunder 2 seconds after you see the flash. How far away is the lightning? You use the same logic. If it took 2 seconds after the flash occurred for me to hear it, and it is traveling at 330 meters per second, then we should have answer B of 660 meters away. So the time delay can actually be helpful in having us understand how far away an object is when it produces sound.